Welcome back to the lecture on convolutional networks. We will start to look with how a typical convolutional neural network architecture looks like. And you see it here. So you can see you have the input, and this is this pixel variant of an image. And after that follows a number of layers that is defined here as convolution and pooling. So essentially, it's not pre-specified how many such levels you should have. It could be one level, one convolution, one pooling, one convolution, one pooling. But it could, so that's up to the design of the network. And essentially, it depends a little how complex the image is, how many objects, how many features, because essentially, if you want to model many features and you have many levels of abstraction that what you capture, you need more levels. So we will go into the details shortly. I just give you the broad picture now. So after that, and one can say that that phase is supposed to do the feature learning. So the idea is that the system after these phases have captured the relevant features that you can see in the image. So then the next step, the final step, is given that the features are articulated, then we want to analyze this. And one typical task is to classify the potential objects that can be there, given the feature map. And that part is more or less like the traditional neural networks that we started to look at in the beginning of the week. And the only thing we need to do first, typically, is because the output of this first phase is normally a multidimensional matrix. But as you may remember, for a traditional artificial neural network, then we normally want one feature vector. So actually, and typically, there is a stage in between called flatten, where we take the multidimensional matrix and create a one-dimensional vector. And then, based on that vector, we do the traditional classification. So this is more or less the architecture. So there are a few terms that are important here when we go deeper into these different phases. So convolution, you already heard, you got the mathematical background. There's also something called filter. A lot of people talk about kernels. I prefer personally filter. Because kernel is used in so many fashions, as you remember from earlier lectures. This is a little confusing, actually. There is a concept called stride. There is a concept called padding. All that have to do very much how you handle this convolution layer. And we have the concept of feature map, and of course that's the map of features that gradually is built up, and so on. But we will go through all these concepts systematically in the following slides. So we will start with what is most characteristic for a convolutional network. This is the convolution and pooling phases. And these phases together, one can characterize as the feature learning phase. And the feature learning phase is a network consisting of an arbitrary number of pairs of convolution and pooling layers. And the number and roles of these pairs of layers are engineering decisions for typical problem settings, but in general, later, deeper levels handles more abstract or higher level features or patterns. And that's in analogy with our assumed model of the functioning of the human visual cortex, that also have these layers that systematically looks at more complex features. So now we will focus on what happened in one layer, and we assume that functionality will be the same independently. How many this is pairs of layers we add. So always for this kind of tasks, it's very important to look at what we start with. So here we assume we got images with a certain format in this RGB model. So in this case, we assume we have an example that are 32 times 32 pixels, and they have a 3 pixel depth to handle the colors, shades. Let us now look at the convolution layer. A convolution layer has typically many filters that are going to be processed on the input image, either in parallel or most typically in sequence. Now we will look at what happens when we apply one filter to the input image. And as you understand, what we will do now is I would say a slightly abstract equivalent of what we did when we did these small examples on convolution, because essentially the idea, the way to regard what happens is that we have like the analogy. We have two functions. We have the input, the whole input image, which is one entity. We have a filter, and we are going to view the input image from the perspective of that filter and map that onto another array. So you can say that the output from this face is a new array which somehow should be considered the convolution of the input array we look at and the filter. And it's the filter in a way that reshapes in the same way as the J function in the mathematical function. The J function reshapes F. So here the filter reshapes the input and gives us the output. So, and of course, in every of these steps, one have to choose a particular filter, and a few things to think about then. So first of all, one have to think about the size, and obviously filter is a sub-area. So we have a rectangular input area, and a filter should be some subset of that. And normally we talk about filters of a limited size. They could be 5 times 5, they could be 3 times 3, and so on. And the idea is that also in an analogy with how we calculated the mathematical convolution, we should let actually this filter slide across in a systematic fashion across the whole input array. So let us disregard the color dimension for a moment. I mean, they of course have to be handled, but they just shouldn't disturb the main process for the moment. So let's forget them, and let's assume that every pixel has one value, a number. So when we slide the filter across the total input image, we take the dot product between each filter element and each corresponding element of the sub-area of the input array that we are at the moment. And then we get a scalar out of that, with one number out of that. And as you understand, when we move a filter around, there are so many positions the filter can be in, and normally, depending on the size of the filter, the size of the filter decides how many positions can be, but normally those positions are fewer than what we started from. So when we handled one position of the filter, we calculate the number and we put that number in the new output array. And then we let the filter slide. We do the same computation for that position, we put it in the output, etc., etc. So when we have done that systematically for all positive positions of the sliding, then we have a complete feature output map. And the normal thing is that we have a stride which is low, which means that when we slide, we take 1 step or 2 steps or 3 steps. So a stride of 1, we just move this filter window consecutively. But we could have a bigger step, which means that we will go more rapidly. But of course, there will then also fewer filter measurements, which will also then lower the number of elements in the feature map. So just to summarize then, what we have is a filter, and that's kind of a measurement from a certain perspective. We apply it, we create this output matrix and the size array, and the size of the output array depends, of course, on the size of the filter and the number, the size of the stride, actually. So let's look at another example, maybe go through this, because I think it's important to understand this basic step, because it's the heart of this method. So here is another example. We have a 7.7 array that gives us 49 elements. The filter is shown in the middle. The filter size is 3, and then it's black and white. So now we from the beginning we get rid of the color schemes. The stride is 1. And this filter, and this is a new thing, which we didn't talk about in the last slide, that of course there have to be a certain pattern in the feature, because the pattern in the feature, this is what defines the measurement we want to do. So in this case, it's a filter that is supposed to find diagonal patterns in the input image. So the output, because of the size of the filter and the stride, in the same sense that in the earlier example, we get a smaller output array, actually a 5.5 array with 25 elements. And here you can see, you can do it yourself, so you can place the filter in a certain position, and then you make a pairwise multiplication, and you will see that those multiplication adds up to the figure 4. So therefore you get a 4 in the output matrix. So this is what's going on. And of course there are, in a realistic example, the matrix with pixel is great, there are many steps in this. So it's a complex machinery, but I hope I've given you the picture now that the core mechanisms here are pretty straightforward and not difficult to understand. There is another concept that you hit when you read about this kind of systems, and that's the concept of padding. So one can wonder what that means. But I mean, it's in principle very simple. So you have a image input array, and depending on who you choose your filter size, and the stride length, it can be so that you have difficulties in an appropriate way by the sliding cover all aspects, because it may be so that you cannot make such slides that every element it's taken into account. So one way then is to actually extend the image frame with some dummy elements on the border. Of course, these are not informative because it's just put there to get some space. But if you do that, then you may counteract this the state of the affair that you cannot really measure every corner of the image. It's more of an engineering decision from case to case whether you think this is important, if it's necessary, if it's beneficial, and so on. So there is no clear. It's a context-dependent choice. But that's the concept of padding. That's really augmenting the image frame, image with an extra frame for the reasons I gave you. As I already told you, in each convolution layer there may be many filters. That mean which means there are many kinds of measurements you want to make in parallel on this input image, and these are handled separately. So there's the same process for each filter, and each filter produce an output array. And as you can see from the picture to the right, what we then get when we are finished with going through the all sets of filters, it will get like a sandwich of output arrays. So we get a bigger array actually in the end. The pooling subsampling layer is a complementary step. So I said earlier, normally the convolution step is always followed by some pooling step. And the purpose of the pooling layer is to reduce the complexity of the array you created. So, because if you have many filters looking for many different kinds of features, that will give you potentially a large array coming out from the convolution step. And typically you then want to reduce that. There is an analogy here with what we discussed in an earlier week of overfitting, because if when we talked about decision tree, we said that okay, if a decision tree becomes too complicated, if it includes too many nodes, too many branches, it's more likely that it will do overfitting on the data it's going to test. And it's the same here. There is some parallel here, that you get a too complex array structure here. It's also a risk to get a similar phenomenon. So the pooling layer operates on each feature map. So as we said, out from the convolution step comes portfolio or sandwich of these feature maps, and then so in the pooling layer you do the pooling operation on each feature map independently. Also here you use filters, but for another purpose somehow. But actually you typically also here define a filter with a certain size, and then you move that filter around on the surface of the array you have at hand. And then of course you need to define what kind of matching should take place between that filter and some subregion of the area you're going to study. and one very much used approach is to just pick the biggest value. So out of the big array, you apply the filter window, and then for the sub area you cover, you pick that pixel with the largest figure, and that figure is what you take out as the result from that measurement. And as in the same way as we did in the convolution, you move this filter around with a certain stride also. So as you can see in the example here to the right, you have a 4x4 window, and you have we select a filter of size 2 in both dimensions, and we have a stride of 2, which means actually that there are only 4 positions that this filter can have. So then actually when we go around, we place the filter over which in one of these 4 positions, and if we have this max pooling approach, we just pick the biggest number in each position. An alternative approach is average pooling. Then you take the average value in each little square, and you output that result. So the output here, given this example, is a 2x2 matrix instead of a 4x4. So that's also pretty straightforward. That two aspects of the neuron structures used in this networks for the convolution and pooling layers. So two phenomena is weight sharing and local connectivity. And both these phenomena or aspects are actually attempts to fight the complexity. So for example, it's assumed that when you apply a filter, you should apply it in more or less in the same fashion. Doesn't matter where on a input array you apply it, the behavior should be the same. So therefore, normally you make restrictions on the weight. So you say that the weights of the neurons involved should be the same. Doesn't matter whether the filter is applied here and here. Neurons involved should keep the same weights in these cases. So therefore, I mean, in a normal artificial neural network, the weights could be all totally separate. So there are no restrictions on connection between weights. But in this case, at least for these subsets of weights, for this subset of neurons, you can imply the restriction that should be the same. So the other thing, local connectivity, is also, as you know, that in a general NNA, the neuron connections, any neuron can be connected to any other neuron. But here, because we have this layer structure and also certain neurons applied in a certain filter, then it's also normal that you pretty strictly restrain the connectivity among the neurons involved. So both these things together contribute to making the system more efficient. When leaving the convolution and pooling layers and before entering the fully connected layers, the output of these previous layers is flattened. By this is meant that dimensions of the input array from early phases are flattened out to one large dimension. So you can see a small example to the right, but you can also have a bigger one. You have a 3D array with a shape of 10 times 10 times 10. So when flattened would become a 1D array with 1,000 elements. So this is pretty straightforward. So now we have something that is easily and normally can be put as input to a kind of standard artificial neural network. After the flattening, we move to the fully connected layers. So in contrast to the earlier layers, who primarily did feature extraction. The fully connected layers are supposed to do typically classification or something of that kind. The fully connected layers takes as input a flattened array representing the activation match of high-level features from earlier layers and outputs an n-dimensional vector, typically. So n is the number of classes that the program has to choose from. So, for example, if the task is digit classification, n would be 10 since there are 10 digits. And the fully connected layers determine which best correlate to a particular class. So, and you can have different kinds of activation functions in this layer. You can have the ones we already discussed. But there's also something called softmax activity function, and that's particularly useful for handling multiple class classification problem. So essentially what that kind of activity function ensures is that the outcome, the output in this vector is a sum of numbers that equals to 1. So it's a probability, it gives you a probability for whether the instance you look at, you found an instance in the image is a member of one of these classes. So that can be pretty handy. Finally here, there are a few comments on the activation functions that could be used. So many times you use different kind of activation functions in different parts of this kind of complex system. So if we look at state of the art, it's very usual to common to use something called rectified linear unit activation function in the convolution and pooling layers. It's a very straightforward function and easy to handle, and there are no negative things with you doing that. For the output, you can do different things. You can use what was already mentioned, sigmoid functions, hyperbolic functions, if you have a binary classification problem. For a multiple class classification problem, the softmax function is very popular because you get a normalized input in terms of probabilities for class membership. Sometimes people use also Gaussian functions, but that's not the most common. You can also have an identity activation function, which is recommended for regression problems. Here I will go through another example, and it's also mentioned this example. It's a pretty well-known example of a CNN, actually one of the first real systematically carried out systems of this kind. So it's from 1990, so it's pretty old given the use of this sub-area. And it's a system where the purpose is to analyze handwritten, machine-printed characters, actually. But, I mean, they are in the image form, so they are in form of pixels. So it's still an image recognition problem. So actually you can see here, this is more of a repetition, of course. You can see that there are two of these pairs of convolution subsampling layers, and then it's a full connection area. So one flattening phase, two fully connectors, and finally there is a softmax classifier applied. So here you can see, you also see here clearly how these dimensions vary. I mean, this is of course a key issue here to understand the size of these arrays, so how complex the problem you create. So here it's a grayscale, 32 times 32 grayscale image. That's what you start from. And then you have a collusion layer with a filter of size 5 and a stride of 1. So then out of that you get a matrix 28 times 28 times 6. And then actually you apply a second layer where you reduce both dimensions with the 2 pooling layer. So after that, you have a different kind of convolution. You have a different kind of pooling. So then, in the end, you are down to something that is 5 times 5 times 16, actually. And then you have 2 fully connected layers, an output layer, and in the end, there is a mapping on the digits that is 0 to 9. So here you can see a summary of the system. You can see the different layers employed. You can see the kind of feature maps produced, the sizes. The filter kernel is the equivalent synonym to filter. So you can see the filters applied. You can see the strides. You can see the kind of activation functions. So hyperbolic tangent is a variant of sigmoid. So obviously here, in this very early system, it wasn't so popular to use this ReLU function at that point. So still it was the fashion to use sigmoid-related functions. So this was an example, again, of the same scheme. Finally, I will give you some timeline for what happens in this area. As I said, the pretty young area. Maybe one can say that this LeNet, the one example I showed you lately, is more or less the point where this really took off. There were a number of precursors in the period before. Actually, this area really got famous only at the point where you get more powerful hardware to support the system, because these systems are very complex and takes a lot of computative power. So the existence and the knowledge to apply special hardware for running these systems made a big change. And I would say that the big success story is this 2012 system, AlexNet, by Alex Krzyzewski. So that was convolutional neural networks. I hope you got a fair picture. It's maybe not the simplest area at all, but it's really important component in this whole realm of artificial neural networks. So thank you for attention. It's the end of this lecture. The next lecture, 6.9, will end this week, and it's the lecture is about deep learning and some recent developments. Thank you.